Hello, everyone. I'm Nagoo from Houston, Texas, and today I'd like to share some fairly deep insights into a topic I've been in love with for quite some time now, critical gas velocity, and focus on some key multi-phase flow concepts that I believe is missing in the current understanding of critical gas velocity modeling. Hence the title of what does it actually mean and why it's so important. I'd also like to thank SAGA Wisdom for selecting us as part of their Game Changing Tech. So for the first part of the talk, I'd like to focus on what are some common misconceptions about critical gas velocity, and then I'll transition into why this improved understanding is important, and conceptualize and validate our understanding with some key experiments and field data validations, and then finally I'd like to introduce you to the tool that does all of these calculations of multi-phase flow, these automated production calculations of multi-phase flow and critical gas velocity and so on, the MAPe tool, and why it's an exponential technology for providing new insights into production optimization workflows. So what I like to do is, I often like to step back and look at the prize of what we're trying to do here. And in production engineering, we think about this world in terms of the latitude and longitudes of pressure and flow rates. And what we're really after is trying to find out that pressure profile along the well, those individual multi-phase flow characteristics along the well. And particularly in unconventionals, we're interested in things like slugging and critical gas velocities and holdups and so on. But if you really think about what the pressure profile is in a well, it's nothing more than a representation of what you have in the well, the volume fractions of the phases. And all of your flow patterns are just different types of manifestations of what you have there. So the pressure behaviors is governed by the volume fractions, and the volume fractions and the individual phase velocities collectively, that relationship is what we call the well slip behaviors. And that's the key thing that's actually causing you to see the different types of flow behaviors in the well, whether it's a slug flow or an annular mist flow or so on. And that's what you see visually represented in your slip, in the types of slip that you have. Now, the problem is that there's a misunderstanding, in my view, of what's actually happening, in that, when we think about concurrent multi-phase flow, the gas is not actually removing the liquids. What's actually happening is that there's a constant slipping between the gas and the liquids to various degrees, which we call different flow patterns. And, we call that hold up. The liquids will be held back due to that slippage in concurrent flow. But in countercurrent flow, when you have partial or full countercurrent flow, you have both slipping and liquids falling back downwards. And that's a key difference, because you need to have a deep understanding of the two different types of wellbore slip behaviors, which is characterized by concurrent flow and countercurrent multi-phase flow. And this is really where we must start to understand critical gas velocity, because you cannot really understand the concepts of liquids flow reversal without understanding the differences between concurrent and countercurrent multi-phase flow. And there's a large bodies of literature of both, but we tend to see more of in the petroleum industry, the concurrent part. And this is what has always been missing before, and it's a key source of misunderstanding. So when we talk about concurrent multi-phase flow, we're always talking about, whether it's concurrent or countercurrent, we're always talking about liquids accumulation. But in the case of concurrent multi-phase flow, the liquids accumulate in all sections of your wells, and you have this phenomena of the liquids being held back due to the slippage. So you have liquids slipping but not falling, and you have both concurrent flow of positive liquids rate and a positive gas rate. And that's how you develop a holdup profile. But in countercurrent multi-phase flow, you have a new phenomenon, because now you have accumulation due to liquids slipping, still hold up, still slipping, but now it's additionally falling. And now you're going to be building up a static gaseous liquids column at the bottom of the conduit. And that's really, the source of confusion, because the onset of liquids flow reversal, which is what we call the critical gas velocity, it's the start of this countercurrent multi-phase flow process. And that's so you start with partial countercurrent multi-phase flow, and you continue until you have full multi-phase flow. And that's important, because liquids hold up is not static to liquids accumulation. So now that we understand that, we can finally come to an accurate definition of critical gas velocity, which is a gas velocity at which any part of your liquid's flow field starts to reverse direction and fall downwards, not just recirculate, right? So we're talking about falling downwards. And it's a gas velocity at the onset of liquid's flow reversal. But even that is open to interpretation, because what are you talking about? What do you mean any part? And if we start from a concurrent mist flow and we start decreasing the gas rate, we're going to countercurrent multiphase flow in many different ways. And the question is, are we talking about a partial fall in droplet mists? Are we talking about partial fall in annular? Are we talking about a mixture between? And the answer is the critical gas velocity is all of the above. It's a range. It's contrary to popular belief, it's not a departure, but it's a range. It's a point. It's a wide range. It includes all of the starting options for countercurrent flow. And the critical gas velocity depends on your different types of wells that you have. So, for example, a high GLR mist flow well will flow in this regime, but a liquids-rich gas condensate would flow in a partial churn annular flow regime. And the critical gas velocity is the onset, that point just before you transition to your zero cross-section average net liquid velocity. And then your liquid start to have a net zero velocity. A net negative velocity. And all of this happens in multiple ways across a wide range of different transitional flow patterns. And that's important because now we can finally understand why we have slow liquid loading in some wells, and why we have sudden liquid loading, fast liquid loading in other wells. And that means we're accounting for the full range of liquids loaded. And that's an important term, because that's an important differentiation into what we understand by liquids loaded. So it's not just about, what happens here, like a Turner analysis, or what happens individually here, like in a film analysis, but it's the full range of this wellbore behavior. And, it's a very involved topic, so this chart here describes the countercurrent multiphase flow process as you start from mist flow all the way down to your transitional flow patterns that you saw before, then to slug and to countercurrent bubbly and so on. And then your wells, there's a whole concurrent multiphase flow part. This is what you normally see in your flow pattern maps and so on. And your wells, flow in both regimes at different times along the well life and individually along the same well. The difference in the understanding that I created in the critical gas velocity model that I have is that we're able to combine that full range. We're able to capture that full range and look at the upper asymptote of liquids loading and the lower asymptote and combine them. So now that you understand what is liquid loading, now you can clearly say what it is not. So it's not the onset of flooding. It's not the liquids droplet only. It's not the liquids film only. And it has nothing to do with the change in pressure gradient curve or liquids accumulation and so on. Because once you have accumulation, you're already past the liquids loading point. So now that we understand what liquids loading is and the onset of flow reversal and countercurrent multiphase flow, now, that calculation, and if you can get that calculation, how do we conceptualize that understanding into a method, a calculation? And that calculation is very important. It's one of the most important calculations if you're talking about the eventual removal of all of the liquids in your well, which is what the definition of artificial lift is. And I've been using this new understanding in my critical gas velocity equation called the Nagoo equation in many different ways. I have a new methods coming out for a virtual wellbore liquids meter that uses this calculation, a real-time plunger rise velocity tracking algorithm, slugging detector for automated gas lift, and so on. But the most important application that we should care about and that we need to get right, the holy grail, is if we can predict early liquids loading detection and diagnosis. And cost effectively managing your wells means that you want optimized remediation and intervention responses in response to better quality and timeliness of liquid loading prediction. So the prediction needs to come before the remediation, not the other way around, which is where we currently are in terms of our understanding. And I could give you, different figures, broad figures. About 95% of your wells will need artificial lift, or 90% of your wells are liquid loading. But the figure that really matters is this figure here, which is only 20% of your potential well life is going to be freely flowing and the majority of your well life, you're going to need to understand when and where you need to apply artificial lift. And it's a deferred production that's the most costly part of your wells. And if you get this right, if you don't get this right, there's a lot of problems. You might not be in business that long. Your investability equation might change, and you might have reserves right down. And it's something to get right because, we don't only want an analytical, explainable, simple, first principle derived model, but more importantly, we want an inclination and diameter dependent model, and we want a liquids loading calculation that predicts early liquids loading that includes the full range of liquid loading. And those things are particularly important for unconventional wells. And that brings me to this equation, which is the key new equation that I came up with, and I and many others. It's a collaborative study, SP 190921, and it's the industry's first full range liquids loading model, and to my understanding, the only full range liquid loading model that has explicit dependencies on the diameter and inclination. And it turns out that diameter is the strongest effect. And it's well validated against many shale unconventional reservoirs. And when we talk about full range, again, just a reminder, we're talking about all of this partial countercurrent flow, that onset of flow reversal. So, and that's very important to remember because any amount of liquids will load a well, not just it's not just a lot of liquids or a little bit of liquids. And if we have that understanding, now we get that same equation is this red line here. And, if you compare that with your gas well, velocity, you can see, you can begin to use this simple analysis of these two different profiles to find out a lot of things that's going on in your well. So for example, you now have a technical, quantifiable, explicit calculation of where your energy tubing should be from a technical standpoint, not necessarily from an operation standpoint. And you begin to see which different parts of your well has liquids loading and that complex interaction between the fluid dynamics around the bend and so on. And it's not just individually within the well. You can use this critical gas velocity and well gas velocity and plot it for the life of well. So you can look at your life of well liquids loading and calculate precisely on a lift curve where you have your onset of liquids loading, and therefore you can now quantify the lost liquids production and gas production that you can get if a well were to load. And this is a huge advancement beyond Turner and Coleman because, as you know, Turner and Coleman has zero diameter effect and inclination dependence in the critical gas velocity equation. But what we typically see is the critical rate equation, which is the PVT conversion of that, and we sometimes get confused with those two things. So what's the best way to test our understanding, or improve understanding, is to look at very simple cases, both field cases and lab cases of observed onset of flow reversal, right? And here's a Texas Tech experiment where you have, a comparison between the Nagoo equation, the Turner equation, and Coleman equation for a large number of experiments done by Jim Lee and others. And you can clearly see a drastic improvement. Here's a University of Tulsa experiment where the gas velocity was systematically reduced until the liquid loading was observed. And if you didn't have the Nagoo equation, which is the red line, to correctly capture the liquid loaded observation, you would still be above the Turner line and so on. And then not just experiments, it's in real wells. Here's a real well profile. And what we expect is that in some cases, for example, in smaller diameters, you can just coincidentally have the Nagoo equation and Turner equation coinciding. It's not much different. This is 1,000. This is, and 1,400. Coleman will always be less. But the real value comes in when you can see significant differences. For example, this is a SPE dataset that they recently released. And you can clearly see, there's a huge difference in the Nagoo equation and Turner and Coleman equations. And you can capture that very precisely. So you can finally forecast critical gas velocity and onset of flow reversal. And it's not just, US wells as well. There's a lot of different papers, different types of diameters, sometimes large, very large diameters that you can, finally get this thing correct in terms of the actual observed loading. And, there's a continuing effort. This is an independent validation of the Nagoo equation, in an Aramco paper. And, just to keep in mind, there's also the annulus multiphase flows as well, types of validation. So beyond prediction, there's diagnostics, so you can diagnose what's going on downhole, and you can see the differences between slight loading and severe loading. In terms of remediation, you can apply gas lift. So in this particular Eagleford 3-phase gas condensate well, water well, the gas lift, when applied, didn't really solve the liquid loading and the lateral loading. And of course, there's the tubing calculations that you can make as well, and you can find out precisely at what angle your different critical gas velocity would matter. My final portion of the presentation is to introduce you to MAPe. MAPe stands for Multiphase Analytical Prediction Engine. It's the V7, it's the newest version. There's a lot of things that's changed. In case you missed it, there's now the possibility to run thousands of wells, all of these different wellbore simulations very quickly. MAPe is all about 80-20% workflow optimization. So we used to live in the world where simple correlations or niche calculations was important, but now we live in a different world where the technology is only a part of the bigger picture, and automation and the time gains from workflow optimization really matters, and that's why you need analytical tools. And automation means democratization as well. So the difference between MAPe and other codes, it's the VBA code is all open. It's a huge head start. So you can think about it as the Raspberry Pi of production software. It's a canvas. And what I'm focusing on my time on these days is just making a lot of MAPe YouTube videos showing how to use these automated calculations. So it's important to keep in mind that yes, you can solve everything, throw the kitchen sink at everything, and take a bunch of different wellbore models and combine it together. But the real value, but if you don't understand what's going on a well-by-well basis, combining those things doesn't really add value. You actually decrease value. So MAPe's disruptive mission is to improve and optimize and automate those production workflows at the well level. And the improvement comes both from the fundamental deterministic theory, as well as, in many cases, MAPe's technology far exceeds what you have in the industry right now for individual things. It would be remiss of me to say that, MAPe's also has a lot of unique things that are based. It's also based on it also has the world's largest validation database. So it's many individual things and incredible things all coming together to make a disruptive advancement in analytical automation-friendly production workflows. And that's that in combination with a much better understanding of critical gas velocity is how we're going to have a baseline understanding for science-driven, data-heavy production optimization at the well level. And with that, I'd like to say thank you, and I'll be happy to answer any questions.